Ladies and gentlemen, my name is Rudolf Rabenstein. I come also from the University of Erlangen, from the same department as Robert, and he got me interested into molecular communication, and he reported about work that he has done in this area, and I report about work that I have done in completely different areas, but that might be interesting also for molecular communication. And I carry on more or less with a model that he used for the enzyme reaction. And let's see. Okay. So here is a short table of contents. I will shortly talk about the communication channel, which is a review of what you all have already seen. We'll have a look at this Michaelis-Menten model for the enzyme kinetics. Then I will talk a little bit about operator theory, introduce a Sturm-Liouville transformation that we have used before, and very briefly a report about an application in acoustics that we have done, and then return here to the enzyme model, show a very simple example of this Michaelis-Menten model, and then conclude with summary and outlook. And this will be a long list of topics that could be done, but haven't been done already. Okay, there has been a recent proposal that Robert just had reported to reduce the intersimple interference by enzyme reactions. And the classical description of these enzyme kinetics is the so-called Michaelis-Menten model without diffusion terms, because it is usually classically used for the production of some material which is in a well-steered container, and then you want to know what outcome of a product you have. And this is well studied, and there is classical literature. This Michaelis-Menten model is a system of ordinary differential equations, and they are tractable by a perturbation approach and certain approximations. And the traditional, well, this perturbation approach allows to separate the short-term behavior from the long-term behavior of these nonlinear differential equations. And whether you are interested in one or the other, you get simpler equations. Simpler nonlinear equations, maybe simpler linear equations, maybe just algebraic equations. Traditionally, the interest has been in long-term behavior, because you want to let your reaction run for a long time to get a high yield in a product. But for biology, it has been noticed before that the short-term behavior is important, and also here we are interested in transience and not in any steady state on the long run. And the question here is whether these mathematical tools for the simpler Michaelis-Menten model without diffusion, whether they can also be used here with a diffusion model, or maybe with diffusion and flow and maybe other nasty things that can appear. Okay, here is the channel model. Again, you have seen this before. A difference is now that I'm considering finite volumes here. So we will talk also about the boundary here. It is not an infinite region. There is the source, and here is the receiver, and they encode a bit stream and they try to recover them again. And inside we have this enzyme reaction that Robert introduced, and here is the chemical reaction. Source, a substrate plus enzyme is converted into some complex with a certain rate K1, and then it decomposes again in the reverse direction, but also in the forward direction with different rate constants into the product P. For our purposes, P is just waste, since the receiver is not sensitive to it. This is the idea. So these are the chemicals, substrate, enzyme, complex, and product. We will not consider the product anymore. And these here are the concentrations of substrate, enzyme, and complex as function of space and time. So this is again the reaction and the Michaelis-Menten model here for the concentration of substrate, enzyme, and complex is shown here. It is a set of coupled differential equations where we have here the term that describes the diffusion. When there is no diffusion, the Laplacian here is 0 and the terms vanish. This column describes the complex formation. This is the upper arrow here with rate k1. The next column describes the complex dissolution in the reverse direction with the rate constant k minus 1. And this column here describes the complex dissolution in forward direction with k2. There is no differential equation for P because we are not interested in P, but there is U, a rate of substrate release at source S. Classically, the Michaelis-Menten model is formulated without these functions just as an initial value problem. But we have repeated releases, maybe not only as impulses, maybe as somehow shaped time functions, and this is considered here by this function U. You may measure these quantities in moles per volume or something similar. Molecules or volume or whatever. For our purposes here, I introduce a matrix representation. We have 3 equations, so we can gather them together in a vector of several concentrations. This is the time derivative. This is the Laplacian. This is now the diagonal matrix of the respective diffusion constants. Here, this vector includes the dissolution of the complex in forward and reverse direction because they differ only by the rate constant. This vector is the formation of the complex depending on the product of S and times E, and this is where the nonlinearity comes in. And this is the input function for our case. Now, we introduce here a vector of concentrations, a diagonal matrix of diffusion coefficients, and we increase here this term, which is only dependent on the complex, by a matrix A, which also accounts here possibly for all components of C, and also this vector here for the product of S and E is denoted by B. U is a vector U where we only have one component because the transmitter only releases substrate and nothing else. Then we can combine these terms. This product here is written more general here as a quadratic form with a matrix that just picks S and E. This is not unique, but for reasons of aesthetics, I have taken a symmetric form in case we have to compute eigenvalues or something. Then this is the Michaelis-Menten model in matrix representation. Here are the time derivatives, here are the diffusion terms, here is the term that results from the dissolution of the complex, and here is the nonlinearity in this quadratic form. This is the input function. And of course, in this general form, it can describe also other types of reactions, because here you see that these matrices are sparsely populated. If we have more complicated interactions between the components, then they are also covered here by the same model to some extent. Okay, now we can come back here to our bounded region where everything happens. including time and space variables, I rewrite this matrix vector equation for the Michaelis-Menten model, which now is valid in the complete volume V here. And I split it for the following slides here into a linear term, which includes diffusion and the dissolution, and this is all a linear component. And this term, the quadratic form, this is the nonlinear component. Don't confuse this latter with the normal distribution. It is just the nonlinear operator here, but it's not a differential operator, but it's nonlinear. Question?
Will there be noise included in the channel description at a later point? You're not. I mean, you're working with deterministic partial differential equations, and I thought the noise came either from molecular diffusion or from the counting process or the release process, and all of these are, you're just using a mean field so far.
This describes the enzyme kinetics. And then when you measure concentration, you might not be able to exactly measure this concentration here. And in the last part of the talk, I shortly mentioned some thresholds, some sensitivity of the receiver where I consider that the receiver possibly cannot detect arbitrarily small concentration differences due to noise or whatever. If you actually need a receiver signal here, you could add a noise term and then obtain a noisy receiver signal if you want to. But this is so far not included here. First, you have to have the concentration as such, and then they're corrupted by noise.
If you're interested in cellular systems, you don't have concentrations. If you're looking at the postsynaptic density, the average number, and you're signaling with calcium ions, the average number might be between 1 and 10, maybe 1 and 100, and it doesn't make sense to talk about concentration. And now you have nonlinear bimolecular reactions whose rates are going to be, a series of delta functions. So I think this, you need to be clear about what framework this applies to. Maybe some macroscopic system where
you might have 1 to 10 molecules, but you also might have more if you talk about longer distances. But also, it's the question whether a particle model is appropriate or whether such a concentration model is a good approximation for the behavior of countable particles. And Robert has shown pictures where particle simulator and his analytic curves coincided very well.
But that was a linear model.
That was a linear model.
And this is a nonlinear. So
yes, but if you talk about 10 molecules, are they linear or nonlinear?
the probability of binding to the sub. I don't want to hold up your talk.
Yeah. There are also investigations on down to what particle number such differential equation models hold. There's the paper by Wolkenhauer and others in NanoBio, I think 10 years ago, and down to a very large quantization step. Due to a low number of particles, they still found that a continuous model were reasonably well. This is debatable, of course. I'm using this, I'm presenting this. If you have not more than 10 particles, you might want to disregard this. Okay, Robert talked about infinite solutions where you have infinite domains where there exist analytical solutions, free field. I'm introducing here a concept for bounded domains, and in bounded domains we need boundary conditions, and the usual boundary conditions that are considered as, in our case, a constant concentration, which might be inhomogeneous, or maybe a gradient of the concentration. If this is inhomogeneous here, or homogeneous, then it might, this boundary condition of the second time with the zero gradient include that there is no flow of particles beyond the boundary. The probably most realistic boundary condition is this one, the third kind, which says that there is a certain flow of particles over the boundary which is dependent on concentration differences. And this is valid here on the boundary, which I have shown in a little bit more detail. Okay, this is the continuous model, and it is shown here. This is well studied, as I said, if there is no diffusion. Well mixed environment, you have a steered reactor and so on, and you can read about this in the literature. I'm referencing here a book by Murray, but there are many others that describe this model. So here you can, without delta, you can distinguish between short and long-term behavior, separate them into different, simpler approximations. Possibly steady state approximations are used in case there is some constant long-term behavior, and there are also analytic solutions for simplified cases. And here the question is, can we include this partial differential equation model? Can we utilize this set of well-developed mathematical tools and approximation also here for our partial differential equation? And the approach I will present here is from a different field that we have worked on, where we have drawn on classical results from operator theory from mathematics. So for the moment, we only consider here the linear part, and for the moment disregard the nonlinear one. The idea now is to project this vector of concentrations onto a set of spatial basis functions. And these spatial basis functions shall be constructed in such a way that they match our problem, our volume, and our boundary conditions. This is the idea. So we may write here the expansion coefficients here. I write this as a transformation because this somehow resembles the calculation of Fourier coefficients. Or you could also write it as a scalar product, where you have a scalar product of the concentration and the basis functions. And the question is how to determine this transformation kernel according to the problem at hand, and how we obtain a set of ordinary differential equations for these coefficients. The idea is to get rid of the spatial derivatives, and then we are with ordinary differential equations, in the end possibly nonlinear ones. Okay, now we have to go into a little bit detail, which may be well familiar to those who know about operator theory. On the left-hand side of our Michaelis-Menten model, or our generalized one, we have the time derivative, and the time derivative carries through to the expansion into the spatial model. It's not affected here by our expansion into spatial basis function. So now for the space derivatives, here the linear model, I omit the dependency on t, and then we need the transformation of this linear part of our operator L acting on C. And since it's a sum, we can split it into two parts, where here we have now the Laplace operator inside this integral, and here we have a matrix A inside this integral. We also have boundary conditions to consider, and we do this by Green's integral theorem. So writing the first part here, by the virtue of Green's integral theorem, we can shift the Laplace operator from the concentrations here to the basis functions, and we obtain a term which is only evaluated on the boundary, and this is where the boundary conditions will come in. And I consider this term now, and I abbreviate it by R over bar here, because it's in the domain of our so-called frequency variable beta, and we will worry about these volume integral later. So these boundary conditions here, this boundary term, they shall be expressed by the boundary values, because we have to assume that they are given. In most cases, they will be 0 if there are homogeneous boundary conditions. So we consider now the 3 cases. Assume the concentration C itself is given on the boundary. Then we can evaluate this part here, and this is how it looks. And this is true if the first part is 0, if k is 0. This set of basis functions k so far is at our disposal. So we can require that it vanishes on the boundary, and then we can incorporate these boundary conditions very easily. The same for boundary conditions of the second kind. If nabla of C is given, then we can evaluate this part, and the second part vanishes if nabla of K is 0 on the boundary. And similar, it can be shown that also for boundary of the conditions of the third kind, the boundary term can be evaluated if certain boundary conditions for K hold. Comparing the boundary conditions on the left-hand side, and on the right-hand side we see that the boundary operators are the same. So we see that from the given boundary conditions for the concentrations, we can infer directly the boundary conditions that our basis functions has to fulfill. Now we go back to the transformation of our linear operator, and we see that the Green's integral theorem has shifted here the Laplace operator in blue from the concentration to the basis functions. It's got to go somewhere, and this step here is the parallel of integration by parts in one dimension. The Green integral theorem generalizes this to higher dimensions. Here is our boundary term, and here is the linear term of the concentrations. Now, since delta Laplace operator of C is replaced by C here, we can combine the two integrals, and then we see that another operator holds for the eigenfunctions k here, and this is the so-called adjoint operator. So we would like to simplify this integral here, and still we have the basis functions at our disposal. All we have set so far are the boundary conditions, and now we require that these basis functions are given by a boundary, by an eigenvalue problem, because then we can replace this integral by the projection of the concentration to the basis functions, or by these coefficients that we have given here. So the transformation of the linear part turns into the coefficients without transformation multiplied by beta squared. This corresponds to something like a differentiation theorem of the Fourier transform, plus the boundary term, which would vanish for homogeneous boundary conditions. How should we now determine the boundary, the transformation kernel? The answer is solve this eigenvalue problem subject to the boundary conditions. Both are determined now. To go back to the spatial domain, if we want to do this, we have to consider that there are two eigenvalue problems, one for the linear operator and its adjoint. The solutions can be shown to be valid for, possible for a discrete set of eigenvalues, and then there result two sets of eigenfunctions which are B orthogonal to each other. And this leads to a generalized Fourier series which allows to recover the concentrations in space and time from these coefficients and the adjoint basis functions. if we wanted to actually do this. And by the way, we have not considered the nonlinear term so far. Before we do this, let's have a look at the linear problem. We have now this linear problem here with the boundary conditions converted into a set of ordinary differential equations for each value here of this eigenfunction. So we turn the input signal, possibly the inhomogeneous boundary conditions, boundary values, into this domain of the basis function, solve a set of ordinary differential equations, and if we want, we can recover the concentration. However, recovering the concentrations here is not my main concern, because this means solving partial differential equations. That we could use software to do this. We will stay here and see whether we can actually analyze and draw conclusions from these ordinary differential equations. So here is a structure that shows that we actually can recover the evolution of these coefficients here from the input signal and boundary conditions by a relatively simple block diagram first order. And it becomes even simpler if we stack all these coefficients for all possible sets of mu together in vectors, or here into a matrix, and then we have a very simple matrix ordinary differential equation, and here a very simple block diagram. And now we can also consider the nonlinear term. It involves some calculations. The transformation of the nonlinear term means we have to include this quadratic form into this integration. We can now replace the concentrations by their expansions into the coefficients, as we have seen before. And then by sorting the integral and so on, we obtain a double sum over the product of the concentrations for different indices, plus a function which only depends on eigenfunctions and the vectors and matrices of our model, but not on the actual concentrations anymore. And we can write this also in a vector notation, and then also the nonlinear term in the domain of these coefficients here is the quadratic form of the respective vectors. So we can summarize the full problem. Here, this partial differential equation with boundary conditions is converted into a set of coupled ordinary differential equations which look in vector matrix form like this, and the nonlinear term here pops up as an additional branch with a quadratic form. That's it. This can also be extended to so-called inner boundary conditions or contact conditions. For example, if there are cell membranes with a certain permeability, then we can define transformation kernels for the complete domain by considering these contact conditions in the same way as the boundary conditions are considered. Okay, we have been doing this for quite a while, and I just want to spend this one slide here on the previous application just to show you that this mechanism actually works. This is the differential equation that describes the vibrations of a guitar string, and in addition, not shown here, we have also considered the tension nonlinearity of the string for high if you excite the string very hard for high deflections, and this is a software synthesizer where this mechanism is built in, and this is how it sounds. This is not a mathematical proof, but it shows that there is a reasonable output from all this mechanism and all these equations. So, back to our Michaelis-Menten model. The idea, maybe I should go back here, the idea is to study these differential equations, these ordinary differential equations. There is no diffusion term. The diffusion is somehow coded into this feedback with the discrete eigenvalues for the different modes of the diffusion. And, okay, for each single value we have one set of ordinary differential equations. Altogether they represent the diffusion problem, and the idea is that we have a finite number of modes of values here, a finite size matrix which describes and approximates the problem reasonably well. And this also happened in our acoustic application. So here I just want to show some simplified problem that I have done with this classical Michaelis-Menten model that has no diffusion terms anyway. So with some initial concentration, and here an assumption that the total amount of enzyme is constant because it's either free or in the complex, but the sum is constant. And the other assumption is that here the amount of released substrate is much smaller than the amount of enzyme, and then we can reduce the number of equations because we don't need an equation for the enzyme. And with the second assumption, we can separate the behavior in short and long time behavior. Only the transition is of interest because the long-term behavior of the substrate is that the substrate is zero, because on the long term all the substrate molecules are eaten by the enzyme. And in the simplest way we can do a first order perturbation approach, and then we have here an example result. This is a little bit similar to the curves that Robert has shown, and there is also another paper which also investigates here the shape of these of these injections. And so we see that it might happen that after a long series of injection, we have a long series of ones, and then the total concentration increases, and in the other case we have no injection for a long time, and then we have one injection from 0 to 1. We run into trouble with detecting this single injection if possibly from previous injections here the concentration is higher than this injection, because then we cannot distinguish between whether the last one here is a 1 or is a 0. So I demand here that still in this upper case we have a lower concentration here than after one injection after a long series of zeros. And then you can show that this is just a sample result.
If we don't move on to the last slide, we're going to run into dinner, so perhaps we can...
This is the last slide. Okay. Yeah. Okay. We can show that the maximum injection rate is given by a rate constant and the sum, not the sum, and the product with the total amount of enzyme. So from the rate constant and the amount of enzyme, we can control here the simple frequency. Okay. Now, what have we got so far? A model for a system of reaction with 3 components, possibly more if we make the vectors longer. The Michaelis-Menten model is included here, but for other entries into the matrices, we may also have other types of chemical reaction that take place. We have formulated this as an initial value problem, turned it into a set of ordinary differential equation where the second order nonlinear behavior was included as a quadratic form. There were no steady state or quasi-steady state assumptions required because we never know at a certain point whether we actually have at this point in space a steady state behavior or not. But if there are any conservation laws in the complete volume, we can consider this by suitable boundary conditions. And we have seen that boundary condition of 1, 2nd, 3rd kind can be considered. Contact conditions can also be considered. Nonlinear diffusion, I did not talk about this, is possible in the same way. And flow terms can be considered by an advection term which changes the linear operator and its adjoints. You have seen example applications, and I have shown in a very simple analysis what can be read from these nonlinear ordinary equations. Of course, such an analysis would have to be made for every single mode in the system. And the question that I want to pose here, whether this application may solve problems in molecular communication, and we have seen one critical voice already. Thank you.